I understand it's a terrifying weapon, but the details of how it works are beyond me.
What are you talking about, Oliver?
I've been researching atomic bombs. There was this special feature on TV about atomic bombs, and I felt that we should just know more about them for the world peace.
Oh, that's a brilliant thought, isn't it? In the world using atomic bomb. I think the desire to learn about the atomic bomb is incredibly noble.
Thank you. But I've been trying to study it properly and have been researching various things, but it's so difficult that I feel like giving up. I've heard of uranium and other things, but there are too many technical terms, and I just can't understand it at all.
Well, it is true that the explanation of atomic bombs is often quite complex, making it difficult to study.
That's right. If you don't mind, could you teach me in a way that I can understand too?
Sure thing. Well then, I'll explain about atomic bombs this time.
Looking forward to knowing about it. So, what exactly is an atomic bomb?
To understand atomic bombs, first, you need to know the structure of an atom.
What was the structure of an atom like? I learned about it in the past, but I don't remember it very well.
Let's go through it step by step. First of all, the premise is that atoms are the fundamental building blocks of this world. Whether it's water, iron, air, or even Oliver and me, if you break everything down, you would understand everything is composed by atoms.
So, everything is made up of atoms at its core?
Exactly. And atoms, when further broken down, consist of a nucleus and electrons. Furthermore, inside the atomic nucleus, there exist protons and neutrons.
Even if you say that, I still don't quite understand.
Let me explain it step by step. First, let's talk about electrons. Simply put, electrons are what move when an electric flows. When you charge your smartphone, there's an exchange of electrons happening. Whenever we talk about electricity, electrons are always involved.
Got it.
And electrons exist around the nucleus of an atom. The size of the nucleus is about the size of a baseball compared to the entire atom being like a baseball dome.
An atom is mostly empty inside, a hollow, empty thing, you could say?
Well, that's about right. And inside that nucleus, there exist protons and neutrons. Protons carry a positive electrical charge, while neutrons, as the name suggests, are electrically neutral, meaning they carry no charge. By the way, the electrons I mentioned earlier carry a negative electrical charge.
I wonder what positive and negative electricity mean.
Simply put, it's similar to the N and S of a magnet. When two positively charged or negatively charged objects come close to each other, they repel each other. On the other hand, objects with opposite charges, like positive and negative, are attracted to each other. Indeed, just like magnets repel each other when north and south poles are brought close, but attract when N is brought near S, the positive and negative charges in electricity behave similarly to the N and S poles in magnets.
Absolutely. It's fascinating how the dynamics of positive and negative charges mimic the behavior of N and S poles in magnets. It's like the electrical world and the magnetic world share similar principles.
That's true.
But if that's the case, it feels odd that protons are packed inside the nucleus. If a lot of protons are gathered in a very small area, called the atomic nucleus, wouldn't they repel each other and cause the nucleus to break apart?
Oliver, you have a good eye for detail. Indeed, as you mentioned, the protons are experiencing a strong repulsive force, trying to move apart from each other. However, the reason why the nucleus doesn't disintegrate is due to the presence of a force called the nuclear force.
Nuclear force?
Nuclear force is very strong between protons and neutrons, neutrons and neutrons, and protons and protons. It's the force that pulls each other together and tries to stick together. As I mentioned earlier, indeed, protons repel each other with a strong force and try to move apart. The nuclear force is a much stronger force that tries to bring the protons together, so the atomic nucleus doesn't fall apart.
Wow, so there's that kind of force? Nuclear force? I might have heard of it for the first time. But if it's such a strong force, why don't we think about nuclear force in our daily lives?
That's because nuclear force only operates at extremely close distances. Nuclear force only works when protons and neutrons are closely packed together. For example, even if atoms are close to each other, as I explained earlier, since the size of the atom is much larger than the size of the atomic nucleus, there is a considerable distance between the essential protons and neutrons, so the nuclear force does not operate. Therefore, in our everyday life, we don't have to worry about the presence of nuclear forces.
I see. So it's strictly a force that works within the atom itself, which means it doesn't play a part between atoms, and that's why we never feel the force from the nuclear force.
Exactly. As a matter of fact, the reason why atomic nuclei don't just fall apart is because the nuclear force is stronger than the electric repulsion, as I explained earlier. However, when the proportion of protons in a nucleus becomes too high, the repulsion caused by electricity can sometimes become greater than the nuclear force. Therefore, as a general trend, when there are more protons inside the atomic nucleus, neutrons increase accordingly.
So does that mean the more neutrons in the atomic nucleus, the more stable it becomes?
Well, it's not necessarily always the case. When there are too many neutrons, it can also result in instability. Essentially, it boils down to finding the right ratio of neutrons to protons.
Oh, I see. Why does an excess of neutrons lead to instability, though?
To answer that question accurately, we'd need a complex explanation about quantum mechanics, so let's explain it using the results. First, as a premise, it's a fundamental property of the things in the world to move towards a stable form. Consider this as a fundamental principle of the universe. Let's assume that the greater the number of neutrons, the more stable the atomic nucleus becomes. In addition, considering the premise that everything in the world tends to move towards stability, a scenario where atoms with an infinite number of neutrons should be created.
Certainly, I agree.
But in reality, there are no atoms with an infinite number of neutrons in this universe. I think this can also be deduced from the fact that there are no atoms of visible size.
Right? I've never heard of palm-sized atoms before.
Exactly. Therefore, having more neutrons doesn't necessarily make it more stable. And the balanced ratio of neutrons to protons within the atomic nucleus is roughly fixed, and it's called the stability ratio.
I see. So the ratio of stable neutrons and protons in the atomic nucleus is called the stability ratio.
Exactly. And here, let's consider uranium as the substance used in atomic bombs. Uranium has quite a large number of protons and neutrons, and the total is the highest among the atoms existing in nature. In other words, as I explained earlier, uranium possesses unstable properties due to having an excessive amount of neutrons. This instability is a crucial part to consider when thinking about the mechanism of the atomic bomb.
What do you mean?
Let me explain it step by step. Uranium is an unstable state of an atom, and it has the property that its nucleus splits when given a certain stimulus.
A certain stimulus?
When a neutron collides with the atomic nucleus, uranium undergoes nuclear fission.
I see. By the way, does it have to be a neutron? Can it be a proton or an electron?
Exactly. To delve deeper into it, electrons and protons cannot effectively collide with the atomic nucleus.
What do you mean?
Let's consider a scenario where we try to collide electrons with the atomic nucleus. Since electrons exist around the atomic nucleus, it can be said that the outer part of the atom carries a negative charge. In other words, if we try to collide electrons with the atomic nucleus, they will repel each other due to the presence of surrounding electrons. Consequently, the electrons cannot reach the atomic nucleus.
I see. So it's like the electrons around the nucleus repel each other like magnets. It feels like when you try to bounce the electrons off the nucleus, they get repelled before reaching it.
That's roughly the idea. Next, let's consider what happens when we collide protons with the nucleus. As I explained earlier, the atomic nucleus contains protons, which carry a positive charge. So, even if we try to collide protons with the atomic nucleus, they will repel each other because the nucleus itself carries a positive charge.
I see. So the atomic nucleus repels protons because it carries a positive charge. Does that mean the neutrons, being different from electrons and protons, can collide with the nucleus effectively?
That's correct. When neutrons are emitted towards the atomic nucleus, being electrically neutral, they are unaffected by the positive charge of the atomic nucleus itself or the influence of the electrons surrounding the nucleus. It's easy to get close to the nucleus. Furthermore, when a neutron gets close to the nucleus, it gets strongly pulled by the nuclear force and is drawn towards the nucleus. And being strongly pulled by the nucleus means it gets accelerated more, and the neutron collides with the nucleus at high speed. Subsequently, the neutron is absorbed into the nucleus.
Because nuclear force strongly attracts neutrons, it feels like they stick to the nucleus when they collide.
Exactly. and the nucleus that absorbs neutrons undergoes significant changes in shape due to the momentum of the neutrons. So basically, the nucleus can't maintain its spherical shape and ends up becoming gourd-shaped at a certain moment. When it becomes gourd-shaped, the neutrons and protons in the swollen parts move away from each other, causing the nuclear force to stop functioning effectively.
I remember nuclear force is a powerful force, but it only works at very close range, right?
Exactly. And the reason atomic nuclei don't just fall apart is that the force of the nuclear force pulling them together was stronger than the electrical repulsion between the protons. So, when the nuclear force stops working properly, the electrical repulsion causes the atomic nucleus to split into two. And this is what is commonly referred to as nuclear fission.
I see, so nuclear fission is when the atomic nucleus splits, right?
Exactly. And then, the two nuclei resulting from this split, they fly off in opposite directions at an incredible speed due to electric repulsion. The fact that they are moving at such a great speed means that they possess enormous kinetic energy. This vast amount of kinetic energy is the source of the power of the atomic bomb.
I see.
So-called regular explosions occur due to chemical reactions, but the atomic bomb generates immense energy through nuclear reactions, causing an explosion, and the energy generated by nuclear fission is incomparably larger than regular chemical reactions. Atomic bombs are so powerful that they're in a completely different league from conventional bombs.
I see, so nuclear fission generates considerably more energy than a chemical reaction. By the way, if I understand correctly from what you've explained so far, atomic bombs create an explosion by undergoing a massive amount of reactions, where atomic nuclei absorb neutrons. And this action causes the shape of the atomic nuclei to change and split into two, right?
You're not wrong.
So I have a question. To detonate a nuclear bomb, do we need as many neutrons as there are uranium atoms? Do we need a large number?
No, that's not how it works. Theoretically, with just one neutron, you can trigger nuclear fission in all the uranium and cause an explosion. It's possible to cause an explosion.
What do you mean?
Actually, uranium has the property of emitting multiple neutrons when it undergoes nuclear fission and splits into two. And these emitted neutrons are absorbed by the nucleus of another uranium atom, causing it to undergo fission again. This repeated process of neutron emission and absorption in uranium nuclei triggers a chain reaction. Due to this chain reaction, just by hitting one neutron, an atomic bomb can explode.
I see. So when a neutron collides with the nucleus of a uranium atom, it triggers nuclear fission. And the neutrons produced at that time go on to trigger the fission of other uranium nuclei. But why does uranium release neutrons when it undergoes fission?
I think it's just the way it is. The simplest way to look at it, I suppose.
I see.
Well, if I were to explain it in layman's terms, the ratio of neutrons to protons in the nucleus is generally fixed, as I mentioned earlier. However, in this case, there were more neutrons in the resulting nucleus after the split. You can think of it as if the neutrons are being kicked out of the nucleus, that kind of sensation.
I see, that makes sense.
Well, it's just a matter of imagination. By the way, speaking of the initial neutron required to cause nuclear fission, we detonate a bomb prepared inside the atomic bomb and utilize that explosion to generate neutrons.
I see. Thank you. I think I have a general understanding of how the atomic bomb works from our discussion so far. I have one more question. Is it okay to ask?
I'm fine.
I've heard that people who have been exposed to radiation suffer for a long time because of its effects. But how does that work exactly?
Well, explaining radiation can get quite lengthy, so I'll just give you the overview. Because radiation carries a very high amount of energy, when living organisms are exposed to radiation, their genes can be damaged. You may not be very aware, but a living organism's body is constantly rebuilding itself, and the blueprint for rebuilding the body lies within the genes. And if the blueprint is damaged by radiation, it becomes impossible to reconstruct the body in its original form. As a result, one might develop diseases like leukemia.
I see.
Furthermore, the terrifying aspect of the atomic bomb is not just the moment of exposure to radiation, but also the ongoing exposure to radiation afterwards. Do you understand what I mean?
How so?
Uranium, through nuclear fission, can transform into strontium, which shares similar properties to calcium. Because strontium is similar to calcium, when animals ingest strontium, they end up using it for the formation of bones and other tissues, just like calcium. Also, since strontium continues to slowly release radiation over time, people who have taken in strontium will continue to be exposed to radiation emanating from their own bone. Moreover, animals like cows, of course, as well as humans, process strontium in the same way they do calcium if ingested, which means, for example, that the milk produced by these cows contains not just calcium, but so drinking that milk could result in exposure to radiation, leading to incidents such as contamination.
I see. So, in other words, the atomic bomb damages the genetic blueprint of life, and furthermore, the ongoing impact of the substances produced by the atomic bomb continues to harm the gene, resulting in prolonged suffering for the survivors.
That's the gist of it. There are many other health hazards that occur, but we'll skip those for now as it would make things too lengthy.
I understand. I'll look into it myself later. But still, atomic bombs are indeed brutal weapons. The enduring suffering even after the explosion is just too much to bear.
I really think that's the case. By the way, as of now, technologies like those used to collect specific uranium for atomic bombs and the design of the bombs themselves are difficult, so it's not easy for an individual to make an atomic bomb. But if different methods emerge in the future, we might enter an era where a single person could threaten a nation. In fact, we're entering a time when a 12-year-old kid can achieve nuclear fusion, so I believe we should put more effort into managing information and monitoring the distribution of materials.
Indeed, there's a possibility of nuclear weapons falling into the hands of terrorists. The ease with which everyone can access information has its frightening aspects too. Thank you, Emma. I've learned a lot again this time.
You're welcome. So, here's the summary for this time. Atomic bombs generate explosions through nuclear fission. Everything in this world is composed of atoms, and when atoms are broken down further, they split into nuclei and electrons. Inside an atomic nucleus, you'll find protons and neutrons, and protons have a positive charge which makes them repel each other. However, in reality, neutrons don't just fly apart because the attractive force called the nuclear force is stronger than the repulsive force of their electric charges. And uranium, which is one of the components of an atomic bomb, is inherently unstable. When neutrons collide with the nucleus deforms significantly, and the nuclear force stops functioning properly. As a result, the nucleus splits into two due to electrical repulsion. This phenomenon is called nuclear fission. During the split, the two resulting nuclei are propelled apart by the repulsive force. We are moving in opposite directions with formidable force. And the greater the force, the greater the energy, and this energy causes the atomic bomb to explode.
I see.
That's all for now. Thanks for listening all the way to the end. If you like, feel free to come back and visit again. Well then, thank you for watching.
Thank you for watching, and Albers.